Hi folks, this is a quick introduction to the concept of category. Before we give example, let's see the original definition of category. It's a long definition with many strange concepts. They are so abstract to understand. So let's do some examples first. Suppose we have some cables, video cables. A cable has two ends. Let me write it down. A cable or video cable has two ends. The source end point and destination end point. Here is a cable convert signal from HDMA to VGA. The digital signal flows in the cable in a direction like this. So the source endpoint is HDMA, and the destination endpoint is VGA. Using an arrow, we can express like from the source endpoint, an arrow pointed to the destination endpoint VGA. We call it F. So they're types. HDMA and VGA are types. And F is an arrow. Or in another word, morphism. So an arrow links from the source endpoint to the destination endpoint. Then we go back to the definition. Morphism is essentially arrows. So we have a collection of objects. What's the object? The objects are those types. Video signal port types. Video signal port types, including HDMA, VGA, and we can also have DP, DVI, etc. Okay, those types are objects. And the arrows link from one type to the other. So we have type HDMA to type VGA cable. And we can also have other kind of cables like from DP to VGA, DP to HDMA, DVI to DP, etc. And here is a composite. The composite involves a pair of morphisms. This is a morphism, and this is another morphism with a common intermediate object to make a composition. So we still use the example of cables. Suppose we have, let's write from right to left. We have F. We have G. F is, for example, from DP to HDMI, and G we should lower G. G from HDMI to VGA. The composition is from DP to VGA. That is G circle F. This is a composition. We can't ignore the existence of HDMI because it's the intermediate object, and if we link two cables together, we only concerned about the source endpoint and destination point. The composite arrow has a source endpoint DP and a destination endpoint VGA, and we can ignore the HDMI because it was in the details. When we studied it, when we studied G circle F from a exterior perspective, we don't mind whether there's a HDMI or not. So the effect of G circle F is like a real cable from DP to VGA. They are the same, right? Although it's composited. And for every object, a identity morphism from A to A. What's the meaning? A to A. Since the source and the destination is the same. Originally, we have an arrow from the source to the destination. If the source and destination are the same, are identical, we can link them together like source equals destination, and use a loop F. For every object A, an identity morphism ID A to A. So if we replace A with a type like VGA, so we have the source VGA and we have the destination VGA. Source equals destination. So it's a loop. So from the input to the output, all are VGAs. So this is the ID VGA. That means this cable only contains some cores. But this cable, it involves different types of video ports. So there are chips, maybe here or maybe here, inside the cable to make the transformation of the electrical signals. So for any types of video, we can make cores. We can make cable with only cords, without any chips. With chips. Here, without chips. So it exists. The ID VGA cable exists. Okay, for the objects of video signal port types and morphisms as arrows as cables. Cables. We have those entities. Then consider the axioms, the associativity axioms, and the identity axiom to be required to make it a category. Associativity here is it's a little bit complicated, but let's take a cable for example. If we have 4 objects A, B, C, and D, A like dvi, B like dp, C like hdmi, and D like VGA. Then we have 3 arrows from A to B, F, dvi to dp, B to C, G, from dp to HDMI, and H from HDMI to VGA. Then we make a composition. The composition has different paths. Let's distinguish between using different colors to distinguish them. If we composite G and F, we have G and F here. The composition has an input DVI and output HDMI. And the other composition is from DP to VGA, compositing H circles G. Then consider the paths from DVI to HDMI, and finally to VGA. We have this one. This one can be written down as HGF. And the other one from DVI, we go first F here, and then go through DP to VGA here. So we have a composition like this. It's HGF. Finally, we have 2 paths. This is this path here and this path here, both from DVI to VGA. We expect they are the same. That means if we input the same signal here, we have same output signal here. From the input to the output, make comparison. of different paths, we cannot distinguish which path the real signal goes. It's undistinguishable. So it is required that the composition has the same effect, so they are equal. And go back to the definition. It's here. And finally, there's an identity. This is not hard if we understand about composition. Like if we have f from A dvi to B dp. If we add an idb, what will happen? From A dvi to dp and then to idp, if we expand that, it becomes idb dp f dvi, still dp. So the composition is idb f. And since we have talked that idb maps the same signal, the input signal to the output signal. So the input is the same, the output is same to the input. So it's same to the f, right? And here, IDA, if we expand it, it becomes f dp dvi and IDA dvi. So the composition make it like f equals f IDA. So they are the same. So we get this one. Then it concluded our example of the composition of video signal tables from one type to the other. This is not like how mathematics talking about, right? But if you understand linear algebra, we can convert this example into linear algebra. For example, like let's talk about real linear space. And usually we use a column vector to represent using the volume to represent an element of this space, like 1, 2, 3. It's an element of the three-dimensional real linear space. We also have 4, 5, R2, etc. So consider the linear map from one linear space to the other. Like we have a matrix, I call it F, like 1, 2, 3, 4, 5, 6. And it has 3 columns and 2 rows. The multiplication of the f accepts input x1, x2, x3, 3-dimensional, and because there are 3 columns, and gives 2-dimensional y1, y2. This is a linear map, right? So the f is from 3-dimensional to 2-dimensional. So we require that there is a 2 times 3, 2 row, 3 column matrix F. And if we make a composition G, let's talk about G. G is 7830. It's a 2 times 2-dimensional matrix. So the effect of G is to output Z1, Z2, 2-dimensional from G with an input Y1, Y2. This is G, 2 times G, 2. Can they be composited? They can, because G is here, 2 times 2, and Y is here, Y1, Y2, and 3 times 3, 2 times 3, x1, x2, x3, it's F, Z1, Z2. This is pretty like DP, HDMI, VGA. Suppose a DP has 3 inputs. HDMI has 2 inputs, outputs, and VGA has 2 outputs. The cable can be put together, right? So we can imagine that a matrix is a special kind of cable that has some dimensional input and some dimensional output. The effect of the cable is to make linear combinations, linear map. So composite them together, we have GF. So what is the dimension of GF? It requires a 2-dimensional output and 3-dimensional input, so it should be 3.3. So what is exactly GF? It's essentially the matrix multiplication. 1, 2, 3, 4, 5, 6. This is why multiplication of matrix should have a same call and same columns and same rows, because the columns of a matrix essentially is the input, and the rows are the output. So from here, we have X input. The X is 3-dimensional. So here it accepts 3-dimensional 1, 2, 3, 4, 5, 6, and outputs 2 rows. 2 rows is the dimension of Y, and here accept y as the input with 2 columns, and then finally gives 2 rows as the output of Vj. So this is what mathematics really talks about. And we have a trivial example of the tables, and we have a concrete examples about linear algebra. And the structure, the global structure of these 2 examples are pretty the same. They are categories. Okay, that's enough today.